Okay, this video goes over the optimization homework out of chapters 13 and 14. The first problem was a product mix problem, and you had to add an additional product. So the additional product had hours required for assembly and testing. We had what we can sell it for, the cost of the components, and also the labor cost, which the labor cost is a function of how much we pay per hour plus the hours requirement. So I think I did this different in the class, but this is what the per unit labor cost is, per unit component cost, and then these are the selling prices. We do have a maximum sales. So when you solve this problem, let's maybe start from the beginning, and we're trying to maximize our profit. Total revenue minus my cost minus my labor cost. And I cannot exceed my available hours. I've got used hours. My used hours are a function of how many I make and the hours required to make, assemble, and test. Notice when you do this, you have to extend your problem to include the additional product. Some of you solve this and you set things up, but you didn't change this, and the used hours did not include column E, or the new product. Same thing on your revenue. You have to include all three products. But once you set that up and you solve this, this is the answer you get. It tells you to max out on the XP still. It's still a real good one, and then make the other ones as most you can, but that's still the one that's the most important one, is your XP. It does make fraction computers. That's okay. You could certainly go into Solver and add another constraint if you wanted to force these to be integers. You could, and then solve it and give you a different answer. And again, anytime you add integers, add constraints. Realize the number. This went down a little bit, but you could do that if you wanted to. Okay, problem 14 is a transportation problem. The example we did in class is that we had 3 froms, 4 twos. We were able to determine what the optimal problem was. That was the example. The issue is if we could add additional capacity to our plants so that we had a new capacity, what would that capacity be worth? Well, how you want to think of that is that when you add capacity, you should be able to reduce your supply chain cost. And the delta, if this is the base, you should get a less cost if you add capacity. And then the delta would tell you what that capacity would be worth. So if I had 100 units, now I have a new capacity of 550. And the way I have Solver set up is that my constraint is referencing this new capacity. So when I solve this with the additional 100, my cost right now is $176,050. When I solve it now, it went down to 164. Whoops. It went down to this, so the difference is 11,900. So that's what that 100 units of capacity are worth. I wouldn't want to spend more than that because that's the only benefit I get from a cost savings. So let's take it off this one, put it here, and solve it. And notice the change. There was no change. There's no change. So if there's no change, then there's zero benefit of that. And we knew that already when we solved the problem, the base model, and we weren't using all of our capacity. If we're not using it now, then we're not going to use it in the future, so you're not going to be able to see a reduction in. There's no benefit of adding if that constraint isn't tight. So let's do the last one. we got a new cost that is a little bit less. And it's worth this. So it looks like the best place to invest is in Plant One. It's the biggest reduction, and that's what that additional 100 units are worth in terms of cost reduction in our supply chain. The last problem was a knapsack problem. We had 7 investments. This is what what they require. This is what they're worth. We're trying to maximize our NPV. We can't exceed our cash. We have 15,000. We can't exceed this. So when we solve this problem, the one trick is that you've got some binaries out there. But when you solve this problem, the optimal answer is 1, 2, and 5. That's your NPV. We're not using everything. And then the homework problem, you have 4 different constraints. And so I've set them all up in one setting, and I'll just talk through them. The first one is that you can only use 2 of the first 5. So the sum of that has to be less than or equal to 2. So you can add an additional constraint. If you wanted to, go into Solver, add another constraint that says that this amount needs to be less than or equal to this amount. And resolve it. And so we've limited, we only used 2 of the 5, our NPV went down. And we could continue to do that and just keep modifying these constraints. But let me just talk through them. So the next one is that you can't choose 1 unless 3 is chosen. So that's 3. Or you can't, is that what it was? You can't choose, you can't choose 3 unless 1 is chosen. So that's 3, that's 1, and then you've got to make sure you can choose 1 on its own, but you can't choose 3 on its own. So that's what that constraint is doing, this constraint. That's the left-hand side, that's the right-hand side. That's x1, that's x3, x1. Part C is that the sum of 6 and 7 have to be less than or equal to 1. So that's the right-hand side. This is the sum of x6. You can't choose them both. You can choose at the most 1. And the last one is that x2, if you choose x2, then x1 and x3 have to be there. So if you choose x2, then x1 and x3 have to be selected also. So how can we set that up? Well, what the right-hand side is just x1 and x3. The left-hand side, you have to plug a little trick, and you have to multiply that times 2. So think of, again, this is the big brother, this is the little brother, this is the middle brother, and this is the baby brother. And the baby brother can't go on its own. If I would do this, that's not allowed. I've got to make sure both the big brother and the middle brother go. He doesn't have to go at all, and they can go, and this is fine. But if the baby brother goes, then he has to have both the big brother and the middle brother going with him. Okay, and you just write constraints to tie your left-hand side, which is 2 times x2 against x1 plus x3. Thanks.